Thank you.
Okay, good.
Okay, so hi everyone. Hope you guys can enjoy the lecture and thanks for coming. And my name is Yuping and I'm currently a postdoc fellow at the Maze Lab at MD Anderson. And today my topic is about penalized likelihood in bioinformatics. Maybe not likely. I'm not specifically talking about the likelihood method, but here you should focus on the word so-called penalized. Focus on penalized, the meaning. And I will mainly cover 5 methods: Ridge, Lasso, ElasticNet, SCAD, and MCP. But I will definitely talk about them all. Okay, so this is my content, and let's start. So this course topic is about bioinformatics, or statistical method in bioinformatics. So it's normal that in a typical topics in bioinformatics, people always face such challenges that we always have the number of features P much larger than the number of samples N. For example, the many features, but in terms of like genes or single nucleotide polymorphism, SNP, but few samples. Here, you can imagine that the number of features P here tend to be like hundreds of thousands. But normally speaking, the samples we have are commonly, for example, hundreds or tens. So this is kind of like a highly unbalanced, and we call this type of data as high-dimensional data or high-dimensional data items. So in dealing with such data set, the classical maximum likelihood estimation method is prone to overfit or even undefined. So we need a method based on the existing method that to reduce the variance and control the complexity of the total estimated problems. So, for example, as a real example, for example, the microarray or array sequence, the transcriptomic sequence data, it tends to have tens of thousands of genes, but only normally as a cohort, it will consist of 50 to 200 samples. You can treat here the samples as the tissues collecting or sampling from the patients during the surgery. And the other case is GWAS, the genome-wide association study. So it has up to millions of SNP, the single nucleotide polymorphisms, but typically only a few thousands of samples. So how can we do that? So this is a generalized, penalized likelihood formulation. So we can see the beta hat is the estimated coefficient beta, right? And it is the minimizer of the objective function given below. So the objective function consists of 2 parts. The first part is the minus L. What is minus L? Minus L is here L function is our classical log likelihood functions given different model types. For example, if we are talking about the linear regression or logistic regression or Cox regression, so on and so forth, right? So we can form different type of log likelihood functions. But this is the classical methods. But what we like to focus on in this lecture is the second term, which is lambda omega beta. Here, omega beta is a totally different function compared with the log likelihood function, L. So omega beta is a Pauli function. It can take different forms given different methods we are using. If we are talking about the ridge regression, we may have L2 norm, or as the first example given on this screen. If we're talking about lasso regression, we will take the L1 norm. And if we talking about SCAD, we will the form is quite complex, and I will introduce later. But here is only an intuition that given different type of positive function, the estimation beta hat will behave differently, and it will achieve different results. So the other term, which is lambda here, lambda typically is accepted to be a positive number that used to control the effect coming from the boundary function omega. So this is embedded in the objective function, right? And our target is to minimize the objective function. So the larger the lambda is, which means that we will tend to have a stronger effect coming from the boundary function compared with the minus logarithmic function. So this parameter lambda tend to have a different name called hyperparameter if we are inside the domain of machine learning. So please.
What does that mean?
Hyperparameter.
Thank you.
Okay, so I will introduce these parts in the later of the slides. And the common goal for the penalized likelihood method is there are three common goals. The first one is to achieve the sparsity among tens of thousands of features or predictors or covariates among to see which set or which subset of the features or variables indeed have relationship with the response y. Right? We tend to denote the predictor or covariance as x, variable x, and the response as variable y. So the sparsity means that we would like to investigate what type of, which subset of predictor x are related to the response y. And the other goal is sustainability, which means that, okay, once we are talking about the area of high-dimensional data analysis, because there are so many predictors, and they are compared with the number of predictors, the number of samples are not too big, maybe small, we can use the word. So if the slightly bit of change, the variation of coming from the predictors will tend to have a significant impact on the final estimation results. So given the penalized function, penalized method, we tend to achieve the second goal as sustainability, which means that we tend to we would like to pursue a more stabilized estimation result. Will not change significantly given a little bit change of the input variables. And the third goal is called lower bias on large signals. This is I would like to say the second goal and the third goal are to some extent they share the same similar understanding source. Okay. This is our motivation part. Then I would like to provide an overview of the penalized terms we would like to cover in this lecture. But one term is not included here, which is the group selection, but I will introduce later. So the first penalty term is ridge regression. And does anybody here familiar with the matrix formed here, the norm and the L2 norm, L1 norm? Do you have any sense of how does the equation here, how does the term here look like in detail or in with respect to each element of the vector here? Yes. Oh, okay. I will introduce later. But this is a form. If we treat theta here as the whole variables, right? It is. In here, it is a vector, but in most of the case, we are treated it as a matrix. So which means that it will consist of a group of parameters, not only one, but a group. For example, if we tend to regress the overall cost performance in the our class with respect to the, for example, grade, for example, I will. Okay, so forgive me for a part. So maybe we regress the overall cost performance with respect to the gender, for example, and then with respect to the occupants, or with respect to the locations or demographic features of each student, right? We may collect many predictors or many features, for example, age, gender, and the previous cost performance, right? So these are three predictors. And to regress the response to these three predictors, we tend to have three different correlations, right? And if we make it as a vector, beta 1 or theta 1 here, theta 2 and theta 3, and treat it as a vector, then this is the variable we are talking about here. This is the here the theta s are in vector form. And the detailed expression of these L2 and L1 are known. I will introduce later, but this is only in a matrix form, right? And the first one is ridge regression in L2 norm, and the last regression are in L1 norm. And we will also investigate what is the combination of them. So this is what we call the famous elastic net regression or elastic net pumping. And then we will talk about some advanced pumping here, which is so-called SCAD and MCP. And then we also will investigate the general effect coming from these different type of quantity terms. Okay, so after a overview of these different quantities, I would like to first start with the standardized, so-called standard quantity, which are ridge, lasso, and elastic net. So these three plots provides a illustration, and I can say one of the goal of a class after my introduction, I would like you to have a clear understanding towards these three plots. What does these three plots talking about, and why these three plots can give us a clear illustration towards why these three quantity terms will achieve a very different estimation results. So, okay, I will, as the first look at these plots, I will say, okay, the first one, the very left one, represents the lasso regression, and the middle one will represent the ridge regression or ridge quantity, and the right one represents the elastic net. Okay, our very first iteration is that the lasso regression on the left plot tend to behave like a circle, right? The shape of the colored part of these three plots are quite different. The first one, the first one is a circle, and the middle one behave like not a circle, but a square, and the middle one behave like a circle, and the third one behave kind of like in the middle of these two, right? It's not either a circle, neither a circle nor a square. So how does these different shapes coming from? Where does these different shapes come from? All right. So let's talk about our first quantity terms, or called ridge regression. So the first formula or the first equation provides us a expression of how does the ridge regression looks like. As I previously said, if we treat beta the beta at the middle of this equation as a vector or as a matrix, then the detailed formulation of the L2 norm with respect to matrix beta equals to the summation of the sum of square of each element within the matrix beta. So it is simply, if we are talking about a vector beta, then it is simply the sum of square with respect to each element of beta. So this is so-called L2 norm, nothing special. Okay, so the ridge regression are being first introduced back to 1970s. So it is basically 55 years ago. So it's kind of like a quite old-fashioned quantity terms, but it still behave and it's still being widely applied in the research until nowadays. Right? People widely use such kind of quantity terms in their different topics, and we can notice many publications each year relies on the ridge regression. So in the middle of this screen shows an example here. So if we are talking about the linear regression, right? Here, the first term of objective function in the middle here represents the least square error of a linear regression, right? Y equals to x transpose beta, right? And instead of the least square error terms as the first terms, we adding the quantity terms as the second term. So here the quantity are coming from the ridge regression. So what is the effect coming from the ridge regression? So here I provide 3 key points at the below. So the first point is that the ridge regression will help the coefficient shrink, but seldom goes to 0. I will show it later to see what is the effect coming from ridge regression. And it handles the correlated features well. So it will distribute the weights to each of these correlated features, but will not making each of them becomes to 0. So if you find there are quite highly correlated predictors in your data set, and you do not want to job each of them, then maybe ridge regression is your best choice. So as I said, because none of them will become 0 directly coming from the effect of ridge regression, so no direct feature selection. All remains in the model. So maybe one more sentence. What is feature selection here mean? What is feature selection here means in the topic of penalized mask? Anybody can take a guess? What does feature selection mean? What type of estimation results will mean that we achieve a feature selection result that indicate a feature selection? So okay, so think about what is feature selection. Feature selection, for example, as my previous example, right? The cost, we tend to find out the relationship between the cost performance with respect to the gender and age of our students, right? And we would like to investigate whether there are a combination effect coming from the age and gender and age with respect to the cost performance, or maybe they are coming from only one features, right? So maybe we tend to job one of them, or maybe not, maybe keep all of them, maybe job one of them, maybe job both of them, right? So in the estimation result, in the using the linear regression as an example here, what type of parameter estimation results will mean that some of the features in the data, some of the x of the data will not have relationship with the response y. So okay, so if we, for example, gender, right? If the regression results say, okay, the coefficient with respect to gender are equals to 0, what does that mean? This means that according to our estimation, we found out that gender will not have any effect. The contribution, the incremental, the change with respect to the gender will not have any effect on our response. So in this case, we will say, okay, we realize that, okay, according to our estimation results, we realize that gender will not contribute to the cost performance at all, means that we can drop gender according to our analysis. Right? So this is called feature selection. Feature selection means that we tend to make some of the beta, in this case beta, among the beta vector, some of the beta elements among the beta vector become 0, which means that these corresponding predictors or corresponding feature x will not have any relationship with the response y at all. Then this is called feature selection. But in this case, ridge regression, it will not lead to, it will not directly lead to the coefficient of each beta here becomes 0. So which means that it will not, there's no direct feature selection result from ridge regression. Okay, let's talk about the example here in bioinformatics. This publication, this work is getting published in 2021, so it is kind of like a new public, relatively new research. So in this research, the topic is about the feature cell type specific differential expression, which means that the researcher here tried to analyze the cell type difference given different subgroups. Maybe, for example, in MDNS, we are talking about tumor patients. We are talking about cancer, right? So here, if we're using cancer as a topic, then we would like to investigate the difference of the cell type with respect to normal and the cancer patient, normal people and the cancer patient. Or we can analyze the cell type difference with respect to the different type of cancer patients. Okay, so the data we have is the bulk tissue expressions with multiple cell types. You can imagine that, for example, like we have 20 cell types from the bulk tissues. And we would like to detect the cell type attribute interactions, which the key attribute means, just as I say, maybe you have disease or not, or what type of disease you have, or what, we can always partition the people into subgroups, like according to their, as I said, disease level, or according to their, for example, races or genders or different features. We partition the patients into different categories, and we would like to detect the the cell type specific difference among these subtypes or categories. However, in this data, there exists a high correlation in cell type proportions. I will provide a plot later. So, but before getting to the next slides, I would like to make sure that we follow the notation here. So as usual, Y is used to denote the bulk omic measurements, or we can simply treat these terms as a response. And the W here is the proportion of the cell type H, or in this case, we can simply treat it as a type of features. Right? This is not a vector, although it is the proportion, but it is not the type of vector. It is not a coefficient, but it is a covariance or feature or predictor. In different domains, people using different words to express the same meaning. So I will try to cover all of those in our lecture. And the X here as a trait. Or for example, we can use the disease stage or age as the representation of the X here, according to the different topics we are investigating. Okay, so this plot basically shows us how difficult this problem is, right? So there's many notations on this plot, but just to forget anything. Just we would like to show here is that there exists a strong collinearity among the interaction terms in this data. So basically, what we can see is that once the covariance of W are getting lower and lower, we tend to have a strong correlation between different cell types in this data set, which means that how to say? So in this data set, the cell types are highly correlated, are strongly correlated. So it is quite difficult to handle such kind of cases, right? So because it is highly correlated, so one common result of the classical maximum likelihood method is that it will overestimate the effect coming from one predictor, but will at the same time will underestimate the effect from the other terms. This is one of the common results. And the other common result is terrible result is that the classical method, of course, given the different case, we need to analyze case by case. But I will only provide an overview of the potential outcomes given the higher correlated features. So one terrible outcome is that the change of the input value, if we change the input value a little bit, and the outcomes may change significantly. And sometimes such kind of results may even lead to very extreme case. For example, it will tend to become like extremely big, and it is unexplainably big, especially in terms of the estimated coefficient. So with the use of ridge regression, actually we can effectively address the problem coming from collinearity. So here is the formulation of this from that reference or from that publication. So the author basically try to group the W, the cell type and the pivot, the interaction between these two terms, W and X, as a nonlinear function. But in order to demonstrate the results, I tend to model them as a linear terms. Right? So as I showed in the first formula, first equation here, we see that the author assumed the response y are equals to the additive forms coming from the interaction terms and plus a y naught epsilon. So here, the additive form are a linear combination or a summation of the interaction term multiplied with their coefficient beta. So our estimation are focusing on the beta here, right? So the parameter we are interested in are beta. So here, the second term is the loss function we are talking about. The first term of the loss function is clearly the square loss or the estimation of the y hat minus the true value, the observed value y, the square of it. And the second term is the ridge regression, is the sum square of each element within a vector beta. As I say, penalized with the L2 norm of beta, vector beta, or in a simple word, the summation of square of each element within beta to avoid a huge variance in correlated terms. So as I said, if you find out there are a strong correlation within the data set, it is always the first choice for you to try to use ridge regression. Although the performance of ridge regression are not that guaranteed, but it is definitely a good first try. So the outcome, what is the potential outcomes? I do not want to show the results from that literature, but using a simple way to explain is that it will have a stable estimation of each cell type's effect, and then all cell types remains in the model, so which means that there does not exist feature selection. Okay, so let's get back to our plot. As I said, this first plot represents the lasso, the second represents ridge, and the third represents the elastic. Okay, we've already talked about the ridge regression. So then we can say something about the different elements on this plot. So basically, the circle here, the black circle on the top right of each plot represents the likelihood function or the loss function, original loss function, right? If you're using least square, then it's the least square error. If you use maximum likelihood, then the black square indicates that the likelihood functions. The different circle here means different values. Okay, the beta on this circle, each dots on this plot represents a estimation. So we have a two-dimensional case only, which means we only have two predictors, and of course two corresponding coefficients, beta 1 and beta 2. So each dot on this plot represents a possible values to these combination of coefficients. Then the dot on the black circle means on the dots on a single circle means they have the same loss function value. They tend to have the same loss function value. And the point more close to the green dot means that the loss square value with respect to the given dot, for example, if we take a plot here or take a plot here, then the value of these points are different. The more close to the green point means that we tend to have a smaller loss function, the original loss function. Of course, if we're talking about a log likelihood function, then it is inverse, or the minus of the log likelihood function, because we tend to maximize the loss function. And if we're talking about the minus of the likelihood function, of course, we tend to minimize it. Oh, so if we neglect the polynomial terms, of course, on each plot, the green point is our result. Because on the green plot, on the green point, the original loss function tend to be maximized. And definitely, this is our result. We denote it as beta hat here. But things are different because we have the bounded terms. So the existing of the bounded terms will tend to change our estimation result. But how does that change? Okay, we just talking about the ridge regression. So I will use the middle plot as an example. Right? Yeah, well, here our algorithms will not only focusing on the original loss function, or represented by the black circle here, but also it will focusing on the color part. So which means that it tends to find out a solution simultaneously closer to the original estimation beta hat, which is represented by the green point on this plot, as well as it try to find a solution that also tend to more close to the 0 point. But here, what we call closer to the 0 point, it will behave quite different, right? Just as the data will help us to define how does the black circle look like, different bounded terms will tend to define how does the colored part look like. In ridge regression, because we are talking about a square, the summation of square. So summation of square, just getting back to the basic algebra. How does the sum of square look like in a two-dimensional case? Isn't it a circle, right? If we define, for example, x squared plus y squared equals to 1, then how does the x and y look like in a two-dimensional curve? It represents a circle around the 0 point, right? And the interaction between the x-axis and y-axis is positive and minus 1 and positive and minus 1, right? This is the shape of this the sum of square, right? So because ridge regression have the form as sum of square, so the behavior of ridge regression on a two-dimensional case is a circle. So basically, in this case, we tend to find a solution that is closer to the green point and also closer to the original point, but in terms of the circle. So in this case, the solution is the red dot here, right? If we talk about, let's see what is the red dots. What is the difference coming from the red dots compared with the green dots? Of course, we can see that if we're talking about the absolute value, then we see the red dots tend to have a smaller absolute value, of course, because here is all positive. So we can just say it's value, right? We have a smaller value of beta 1 and beta 2 estimation. So this is the way, or the dynamic way of ridge regression, the dynamic effect coming from the ridge regression. It will tend to shrink the estimation of each beta estimation, but it will not make it to be 0. Okay, so this is a very high-level introduction towards the ridge regression. Then let's talk about the other regression, and which is called lasso. I have to say that till these days, lasso are still a very popular tool if we are treated as a lasso regression family. Of course, there are more advanced type of lasso regression being innovated days by days. But the fundamentals are not all the same, but are quite similar. This is kind of, I have to say, among the 5 bounding methods I introduced today, lasso is definitely the most popular. Why? I will show it later. Okay, so first of all, I would like to introduce what is a form of lasso regression. Lasso regression tend to take the L1 norm of vector, the coefficient vector beta. Or in detail, it is the sum of absolute value of each element within beta. So still, that's quite simple, right? compared to ridge regression is the sum of square of each value of beta. Right? So lasso regression, or L1 norm, is the sum of absolute value of beta. And still, I here using the linear regression as an example, and we see that how does the lasso regression are getting incorporated into the loss function of linear regression, right? This is the general formulation or the general objective function of our problem. We just adding the positive terms to the original objective function to form as a new objective function. And the key effect coming from lasso regression is that it will create exact zero. As I previously said, when this elements of the coefficient vector equals to 0 mean, it means that these corresponding features or corresponding predictors will be jumped or will be ignored during our analysis. We will explain this result as, okay, this corresponding feature or this corresponding predictor will not have any effect on the final response. Or in a short word, what we call feature selection here. Okay, however, although it is quite powerful in terms of feature selection, but it will potentially leading to the overshrinkage of large signals, which means that it may tend to overperform. Right? Some of the features, ideally, we would like to keep them. However, because the overperform coming from lasso regression, the final results of these predictors are zero, which means that we lose certain amount of meaningful signals. And the third problem is that the lasso regression are sensitive to correlated features. So compared with ridge regression will tend to shrink the correlated features to a comparatively small value, but definitely not zero. However, because we are talking about lasso here, so lasso will try to pick one of them and drop the other, which means that these correlated block of predictors, we only tend to select some of them, but drop the other part. So this means these two are kind of like somewhat overlapping, right? Which means that we indeed neglect or indeed lose a certain amount of meaningful information coming from our data set, which means that we do not fully use our data set to make a more validated model. Okay, let's show an example here. So we are talking about genome-wide association studies, or GWAS, a famous GWAS study. And I'm using a publication from 2009 as an example here. So the problem of GWAS is modern GWAS, or modern genome-wide association studies may involve hundreds of thousands of single nucleotide polymorphisms. And which means that in this case, in the analysis of GWAS, we tend to have the number of features are much more than the number of samples n. And the univariate single nucleotide polymorphism SNP by SNP test tend to ignore the interactions and the multi-collinearities. So if we are analyzing the single nucleotide SNPs from these hundreds of thousands, one by one, pairwise, then we tend to neglect many meaningful informations. So the research I used here, they propose a lasso penalized logistic regression for joint variable selection. So everybody here are familiar with logistic regression, right? I think this is one of the most popular machine learning model or most popular statistical model among the, I would say, at least 100 years. So we all know that for the logistic regression, the response y tend to be a binary variable. Sometimes we denote it as a 0 or 1, sometimes we denote it as a -0 or a -1 or 1, or even -1, right? Okay. So the proposed model will zero out most of the SNP's coefficient, remains a small set of the causal variance. So, which means that the proposed model will tend to select a certain, quite small subset of the variance or SNPs from these hundreds of thousands SNPs. And I will show it later, so see, we can make it as small as possible, as small as you want. Okay, so forget me apart. So this is the formulation of this model. And the first part is the quite classical the logistic transform or sigmoid transform function. We transform the mu plus the x transpose beta to a simple variable called pi here, right? And just neglect this part. And we, because of the logistic regression, right, the log likelihood function look like taking the form as here. So I here means different features or different single nuclei polymorphisms, as I introduced in previous lectures. So if we do not using the Pauly terms, and this is the objective function we would like to maximize, right? So this is the log likelihood functions we are talking about in logistic regression. However, here, because we have so many single nuclei polymorphisms, we tend to select a group of them, so we using lasso regressions. So instead of the original log likelihood function, we adding a minus Pauly terms. Okay, here is a little bit confused, right? Why in the previous lecture we are talking about adding the Pauly terms, and here we're talking about minus the Pauly terms. Anybody have an explanation? Why here the signal is minus, but in the previous slides we are talking about the positive or adding a Pauly terms. Okay, here, please. Yes, exactly. So because in the previous examples, the first term of objective function are loose function, or in that case, it's the square, the least square error, or the squared error, right? So we would like to minimize it, and the Pauly terms, because we would like to shrink the coefficient beta, right? Which means that we tend to make these terms smaller. Maybe not as small as possible, but smaller. So of course, in the previous examples, these two terms tend to have the same effect, right? We would like both of them to be smaller and smaller to some extent. Right? But in here, because and maximum likelihood method, we would like to maximize the likelihood of function, as well as we would like to minimize the Pauly terms. So the effect coming from these two terms are different. So this is the reason why here the sign is minus. As I said, we need to focusing on the effect coming from different parts of the objective functions to decide what type of signs we would like to choose. Okay, great. So, however, yeah, because in here, theta are denoted as a mu plus all of the beta. And we only interested in beta. We only interested in the effect coming from x with respect to our final response, y. Right? So we do not care how does mu behave here. So we only put in the lasso penalty with respect to all of the betas, the p betas inside the entire coefficient space instead of all of them, right? We neglected the effect coming from mu because in this case mu are always treated as a baseline and we do not care about it. Okay, so the effect coming from the lasso regression are quite straightforward. So it will quickly derive most of the coefficient to 0. How does it behave? I will introduce later. But the effect of it will simplify the interpretation of large P settings. Imagine we have tens of thousands of genes, but only a few hundreds of samples. if we keep all of the genes in our model, right, we need to explain it hundreds of thousands of times, right, one by one, explain the effect coming from each gene with respect to the samples. Of course, it's not true, but if we do not appropriately selecting our methods, then this is our outcomes. We need to interpret each of those large P times. But with the help of lasso, we only keep a small subset of the genes or predictors. Then we can largely simplify the interpretation of our model. Okay, so here is the result of lasso. What does this 6 plot mean? So we can combine the left plot with the right plot as one plot, because they are different, but I will only explain it vertically. So the first plot, the y-axis of the first plot are the choose of lambda. As I said, the lambda as a hyperparameter are trying to control the effect coming from the positive terms. The larger the lambda, which means the larger the positive terms will take, the effect will take with respect to the final estimation result. Right? If we take the lambda to extremely big, then what is the possible outcomes? Anyone have any idea? Okay, let me get back to the formulation part. So what if lambda here goes to infinity, the positive infinity, of course? What is the possible result? What is the possible estimation result with respect to all of the betas here, the p betas, if lambda goes to infinity? Anyone have a guess? If lambda goes to infinity, what will happen? What is the possible situation we will face with? So, okay, so maybe give some hints. So here, as I said, lambda are used to control, the effect coming from lambda are pointing to the entire quantity terms, right? And these entire quantity terms tend to shrink or tend to penalize the values of the absolute values of each element of beta. If the lambda are extremely big, which means that a small, for example, if the beta are changing, beta j, as an example, beta j are changing from 0.1 to 1, right? Only minus 0.9 change with respect to beta j, but it will take an infinitely large change to our objective function. We tend to maximize the objective function, but only a small change of beta j will have a significant impact with significant loss of the objective function value, because here is negative. So the possible outcome, if lambda go to some extreme value or very big, then definitely the results we will have is all of the beta j here, beta 1 to beta t, right? All of the beta in the quantity terms will have the result as 0. So which means that all of the signals are disappearing. If the lambda go to extremely large, then which means that we will have the result just looking like none of the predictors will have the response. Will have the relationship with our response y. All of the signals disappear. This is definitely not what we want, right? So okay, so with such kind of idea, then let's take a look at these plots. So as I say, the x-axis of these plots are the value of lambda, and for the plot on the first row, the y-axis means the number of predictors that having a non-zero coefficient estimation result, right? Think about the feature selection. If a predictor have non-zero coefficient, means these predictors are being kept, we assume that this predictor having effect on the response. If it is 0, then no effect. So the y-axis of the first plot means the number of the predictors or number of the features having non-zero coefficient estimation, which means they are kept. They are not being jumped. The number of the predictors that are not jumped according to the estimation result. And we see, as I previously introduced, with the increase of lambda, less and less predictors will have non-zero coefficient estimation. And once the beta are getting lambda are getting to extremely large, then all of the beta here, all of the coefficient here we have are 0. So no signal at all. This is what the plot from the first row talking about. Okay, let's talk about the second. What does this mean? So as usual, the x-axis as the value of lambda, and the y-axis. What is y-axis? Y-axis is the number of the true predictors kept by the final estimation results. Right? So here I will say 0, 1, 2, 3, 4, 5. So in this case, we have 5 true predictors. But with the increase of lambda, we can see that the number of the true predictors are kept by the final result are getting decreased. And it will tend to be 0 if the lambda are getting larger and larger. This is what we call drop some real effect. We lose a certain number of signals. So anybody familiar with the confusion matrix? The true negative, false negative, true positive, false positive here, right? So what does this phenomenon represent here? The ground truth is that these 5 predictors are positive, right? But with the increase of lambda, we tend to drop these ground truth predictor. What does this phenomenon represent in the confusion matrix? It is the ground truth is they are true. They should be kept, but our model tend to drop them, right? This they call false negative, right? False negative. Our result says okay they are negative, but they are not negative. They are positive. Right? They are true. So this is called false negative. We tend to have a higher level of false negative once the lambda are getting larger and larger. So this is a possible explanation. Okay, so so with such kind of mind, then we can see the plot from the last row. The last row, as usual, the x-axis is the lambda, the value of lambda, and the y-axis is the false discovery rate. So anybody has any idea towards what is false discovery rate? Okay, so the first discovery rate is what we call false positive, right? False discovery rate, because it is the ground truth is negative, but we think it is positive, right? This is what we call false positive. Okay, so once the lambda is small, and the estimation result is that everything is here, everything is kept, everything is here, none of them are 0. We do not drop anything. Then, which means that these predictors are negative, should be dropped, but are kept according to our final estimation result. And in such circumstances, which means that the false discovery rate is the maximum, right? We do not drop anything, which means that anything should be negative or positive here. Then the false discovery rate are maximized. But with the increase of lambda, as I said, everything tend to be smaller. The value of the beta, every value of beta tend to be smaller and smaller. Some of them are getting 0, and finally everything is getting 0, of course, the false discovery rates are also decreasing. So which means that we tend to have less and less false positive. So this is, okay, so the first point represented the number of predictors we kept. The second plot talk about the true predictors we kept, and the final plot give us the false discovery rates, or the false positive rate we have, right? So according to these three plots, we can see that definitely the smaller value of lambda are not good, because we tend to have too many false positive signals, right? But if the lambda are too large, then we tend to overjob the true signals, which tend to have a higher false negative. So which means that in the using of lasso regression, we tend to be very careful toward the selection of lambda, the hyperparameter, because the lasso regression will have a stronger, if very strong effect with respect to the final outcome. Right? You can control everything basically. You can finally you can drop anything. Right? This is the effect coming from it, but not ridge regression. Ridge regression will not making anything to 0. If we only talk about the effect coming from ridge regression. Of course, different cases you will have different results, but only talking about the effect coming from ridge regression, it will not make anything to 0. But lasso are quite different. Lasso are very powerful. If you do not carefully choose the hyperparameter lambda here, then the results may be getting tremendously different compared to what you are looking for. So, of course, I will introduce how to choose lambda in our later slides. Okay, let's get back to the plot. So this is ridge regression we have already introduced, and this one are lasso regression. So as I said, with the effect of ridge regression, the final estimation will transfer from the green dot to the red dot here. Then with the effect of lasso regression, it will transfer from the green dot to red dot here. So what does the red dot here? This red dot means. This red dot take the value as 0 something, right? That this is the value for beta 2, and then 0 is the value for beta 1 estimation. What does that mean? This means beta 1 estimation are getting to 0, which means that x1 are being jumped. The effect coming from x1 are being jumped. Or in other words, we tend to explain it as we do not believe that the change of x1 will take any effect on our final response y. So this is the dynamic effect coming from lasso regression. Any questions so far? Okay. All right. So after introducing the lasso regression and the ridge regression, lasso regression, I can get it faster. Okay. So we talk about the effect coming from ridge and lasso, and we see that they are both, to some extent, they are useful, but to some other extent, they are not that useful, right? Especially if lasso are very dangerous to some extent, because it tends to ignore. It behaves so strong, right? So we tend to combine the effect coming these two penalty terms together. Then this gives us the so-called elastic net. Elastic net basically is a combination of lasso regression and ridge regression. And here the alpha as a hyperparameter to control how does these two are getting combined. So why elastic net? Elastic net is more stable than lasso, and the strong feature correlations are still yield sum 0 for variable selections. It tends to behave in the middle of lasso and ridge regression, and it will inherit the advantages from both of the penalty terms. Okay, maybe I will skip this example, and this is an example. Okay, I will skip the example because we've already detailedly introduced the lasso and the ridge. So I think elastic nets are basically the combination, right? We can see the alpha here, alpha taken from 0 to 1, which control the effect coming from these two penalties. So okay, so this is elastic net, right? We can see the color parts of the elastic net are quite weird. Why? Why is it so weird? Because it's inherited the shape both from lasso regression and the ridge regression. So we can see that, okay, we cannot, I would say it's maybe look like a lemon, or I don't know what type of shape it is, but you need to memorize that elastic net somewhat is the will inherit the effect from both of these. And this is somewhat I will recommend in your in your research or in your later studies. Okay, then let's talk about the more advanced penalty terms. So I will only cover two in our lecture. One is SCAD, S-C-A-D, smoothly elliptic absolute division. So okay, the equation here of SCAD is quite complex. It's well, somewhat extreme. Why? Because we need to separate these three the terms into three conditions, and this having a different expression of these of different conditions. It's still weird. Okay, I will not talking about the detail of the expression here, but I will first let you to take a look how is scatter regression, scatter penalty looks like in a one-dimensional case. So the red curve here is the ridge regression in a one-dimensional case. As the previous plot is about a two-dimensional case, but here is only one dimension. And the blue curve or the blue line here represents lasso. Lasso is different as a perfect V shape, right? And symmetric given the y-axis. However, scale SCAD tend to behave very weird. It will tend to pretty flat. It is taking a flat line towards some extent, and we're getting to a curve, right? And then we're getting to a line, right? So why people are designing such weird shape? Okay, let's show an example. This is one of the research in Dr. Wen Yuan's lab, and this is somewhat I'm still working on the explanation of this research. And in this research, it's called clonal structure identification through pairwise difference. So in this research, what we would like to know is a unsupervised learning for homogeneity pursuits of different mutations. Basically, we tend to cluster mutations into different subgroups. So this is a clustering algorithm. And why we would like to using scale, I will skip the formulation part and get into the idea of scale. Okay, this plot. So the first three plots, the three plots on the top of the screen are coming from a Nature publication, which is about giving an idea towards what is clones and subclonal mutations according to a 3 region samples. And we see that the different circles on the plot is using a simple word. Different circle of this plot represent different mutation clusters. We tend to group up the mutations within different circles to become to one value or one index, one cluster membership. So, but how to do that? Because these we can see the dots here are massive. They are massive dots, right? And they're quite spread among these three-dimensional space. And how can we put all of the points in different circles to become different values. This is partially the reason why we're using scat, because you look at the shape of scat. Scat tend to behave like a flat line if they are quite separated beta. Right? The beta here is 0. If we take having a beta here, and which means that the penalty terms, the scatter penalty value of these two beta, the beta, are kind of like a constant value. No matter how we penalize the beta, it will not change if the beta are kind of like having a certain large amount of distance. But once the beta are, the initial beta are quite close, right? For example, one beta is here, one beta is here, then we can see that by making the other beta closer to the beta to this beta, then the penalty terms are starting to decrease. What does that mean? It means that the penalty terms starting to work. So this is the key idea of scat. Because as I said in this part, we tend to group the mutations or the black dots within each circle together, but we do not tend to put everything together. Then of course, we do not know, for example, if there's a dot here and a dot here, we do not expect there are a relationship between these two dots, then we tend to keep them as the same, right? We do not want to do anything towards them. But for example, if a dot here and a dot here, then we tend to make them closer and closer and make them as the same value. So this is the reason why we choose scat, because lasso and the ridge regression, they take effect on the whole space. But scat are only starting to change during a quite close or quite small region of a certain coefficient. It will not change at all, which means that the change of beta will not change the value of the penalty terms. Of course, in this case, the memorized and the algorithms will not do anything towards the estimation. So this is called so-called locally. What does that word say? Okay, so the scat less aggressive shrinkage on large signal help identify truly distinct clonal groups, or it is the effect coming from scat are performed only locally, or not instead of globally, as ridge regression and the lasso regression. Okay, this scat and the MCP. The effect coming from MCP are quite similar to scat, but I will quickly go over this because MCP tend to have a better property in terms of statistical theory, but the effect coming from MCP are quite similar to scat. We will memorize one thing. Once you would like to having some local effect instead of global effect, then the advanced penalty terms as scat and MCP are your best choice. Okay, so this is the overall pictures of these 4 different regressions. And we see this is scat and this is MCP. We see that the shape of scat and MCP tend to at least the dynamics of them tend to become quite similar. Okay, so this is the coefficient task by method. I will skip this part because I must cover the group selection part. Okay, so group selection. This will appear as one of your homework. So pay attention to that, but it's not that difficult. So what does group selection mean? Group selection means that previously we are talking about only one variable, individual variables by variables. Right? We tend to select a certain amount of variables among all of variables, but variables are taking quite equivalent to each other. We do not making any hierarchical structures among the variable selections. But here, if we do not choose them by variables, but we would like to select a group of variables together, we tend to select a group of variables instead of individual variables. Then what can we do? Okay, so a very okay, maybe this quite well formulated answer to group selection as so-called L21 norm, or in this case, I give a case with 36 different parameters from beta 11 to beta 66. Then how can we package in if we treat different row as different group, and we only want to select row by row, not individual parameters. I would like to pursue a result that tell me which row shall be selected instead of which specific parameter shall be selected. Then how can we do this? Okay, this is so-called L21 norm. Basically, we first package each row to a value, just look like this. It is a square root of sum of square with respect to the entire row. And then we vertically sum them up. Right? We first take the square root of the sum of square, then we sum them up. So basically, with such kind of approach, what does this mean? This is ridge, right? This is ridge regression, the quantity terms for the ridge regression, and we kind of like packaging them together by taking the square root and then summing them up. What does the vertical sum up mean? The vertical sum up are lasso regression, right? As I previously introduced, lasso regression are the sum of absolute value. Because this is the square root, of course, absolute value are the same. Right? The absolute value are not changed at all. So the horizontal packaging are ridge regression, and the vertical sum up are lasso regression. With this kind of approach, we can choose row by row instead of just the single parameter scheme. Of course, if you tend to choose column by column, then a similar approach can be applied here too. Okay, so this is the effect coming from group selection. We can see without group selection, and only talking about lasso here, different groups, the different color indicate different groups. Different groups, the variables, the coefficient within different groups will behave differently, right? For example, this one will, among this group, this one will become the last one to become 0. And for example, for this one will even have a jump with respect to a quite large number, right? They are behave quite differently within groups. But with the help of group selection, we can see the coefficients within each group are behave quite constant. They are kind of like similar or the same, right? They behave quite same, and they tend to getting to 0 at the same time. And for the red group, they are the same. So this is the effect coming from group selection. Only changing from lasso L1 norm to L21 norm, and the formulation are given in the last slides. Okay, so this will be one of your homework, and if you lack of the idea towards group selection, then please take a look at these slides and think about how to packaging that group by group, how to package each group. As I said, I would like to repeat. So in this case, we package row by row and select row by row. We would like to select each by row. I want to have the result tell me which row are significant, or which row have effect on the response instead of individual variables. How to do that? Package the groups as a whole and penalize them also as a whole. Package the row by the square root of ridge regression and sum them up. Actually, the group selection have a geometric meaning, but I do not have time to cover it in our lecture today. So I may stop here, and there are also a markdown file. Quan, you submit the markdown files to the Canvas, right? Canvas, right? Okay, so there are a markdown file on Canvas. Which is available for you to definitely take a look, because it will provide a quite critical, it's quite helpful to finish homework question 2. In homework question 2, I will provide a data set for you to analyze, and I'm asking you to perform all of the 5 methods I introduced in our lecture on that data set. And the markdown files will provide you the critical functions to use to finish the question 2. So please definitely take a look, and it will provide you very meaningful suggestions. And so for question 1, and it will have you can inherit the idea from the elastic net and also the group selection. The question 1 is basically talking about a bi-level selection. It will ask you to perform the individual selection and the group selection simultaneously. So I've separated the individual selection and the group selection into 2 different sections, right? But there's a question question in the homework asking you to give me the formulation to make them perform simultaneously. Okay, think about the elastic net. How elastic nets tend to combine the effect coming from ridge regression and the lasso regression. Similar idea should be performed on the combination from individual selection and group selection. Simple work, just putting them together. That's it. So think about it. And of course, I provide a reference. So there are answers in the reference. So if you take a look at the reference and having a quick look, and you will find out the solution. Okay, so that's all of our class. Thank you. 10:45, right? Oh, okay, it's time.